So that is an AC circuit for you. AC, alternating current. Now for this AC, the current I is given to be equal to I naught sine 2 pi ft. That is what the current is equal to. I equals to 2 pi ft. And from here, this I stands for instantaneous current. Instantaneous current. That's the current at every instant that you measure it. Anytime you measure it with your meter, the current you get is the instantaneous current. At every instant, anytime you measure it. Then this I naught stands for the maximum. The highest we have, that's maximum current. Okay, and from here, I can still be equal to I naught sine omega t. The current, even voltage is the same thing. V equals to V naught sine 2 pi ft, where the sine 2, that's the 2 pi ft is omega. So you have V naught sine omega t. So that is the formula there for current and voltage. And I've told you what they stand for. Even the V also stands for instantaneous voltage, and the V naught stands for maximum voltage. Now you might be giving me a question, sometimes, let's say you have AC, maybe an AC, they can say an AC represented by, let's say, the relation V equals 4 sine 900 pi t. And maybe I have to find the peak voltage. Find the peak voltage, which is the maximum voltage. The peak voltage is V naught. The peak voltage is V naught. So V naught, comparing with this formula, V naught equals to 3. Equals to 4 volt. So V naught equals to 4 volt there. Again, because we are comparing with these formulas here, comparing this formula with this one, or we can even compare with this. Comparing it, we can have 900 pi t to be equals to 2 pi ft. Here pi will cancel pi, t will cancel t. So frequency from here becomes 900 over 2, and the frequency equals to 450 Hz. That's if you're asked to find the frequency. So that is how you use the formula to solve. I just gave you how to solve the instantaneous voltage and the rest. Even if it's correct, the same pattern applies to it. So that sinusoidal variation is going to be a sine graph. It's something that will be coming like this. As voltage here, or current with time, it is changing as it's going like this. So the thing is changing with time. It's a sine graph, so that's what we call AC. So it has a peak value, and it also has RMS value. RMS, that's another thing you have to look out for. RMS value of current. When they say something is RMS stands for root mean square value. It's a current that is steady. Root mean square value. Root mean square value. Okay, what does it mean? Let me define it. It can be defined as that steady current which develop the same quantity of heat in the same time. In the same time, in the same resistance. So it is that steady current. So root mean square value of current is a steady current. If you are measuring it with your meter, the steady current is the root mean square value of current. That's one that is steady, that doesn't change. That steady one is the RMS value. So it means that what our meter measures and give us as value of current or voltage, our multimeter or maybe voltmeter or ammeter or whatever, it's actually RMS value it is giving you. It is a steady one that you take, because we know it will surely vary, change, but the steady one there is what we select as our root mean square value. So that is what you should understand about RMS value of current. And it has a formula actually. The RMS value of current is given to be IRMS equals to I naught over root 2. If you are to divide 1 by root 2 here, RMS here will now be equals to 0.7071. 0.707 I naught. So if we divide 1 by root 2, you're going to have that value. So that is it. Then again, having known that this is the formula, anytime I have to calculate RMS, and I said RMS is steady current, the steady one, that will have the same effects, that will develop the same quantity of heat in the same time and in the same resistance. So what it means is any current that is steady during this variation, during this sinusoidal whatever, is what we refer to as the RMS value. So please take note of this formula here. IRMS equals to any of the two. If you are given the peak, because this I naught actually stands for peak value of current. All these formulas, please cram them so you can be using them for whatever purpose you want to use them for. Okay, Sabe. Let's go to the resistance in AC circuit. Now let me draw a circuit and put a resistance there. Or let's put AC first. This is a symbol for AC. Then as you go like this, let me put an ammeter, and okay, let me connect it here. Let me take wire here. So you have Okay, put voltmeter here. Okay. No, this diagram is not okay. Let's see something like this. Then put ammeter, so it will tell us the current that is coming. Then now go like this. Okay. Then here I can have a voltmeter to measure potential difference. Then let's put a resistor here. Then the essence of putting this voltmeter here is to know the potential difference across this resistor. That's the essence of putting it. That is the essence of putting it there. Continue with your wire here. Okay, your ammeter here. Put another AC there. Okay, to connect it. So current enters, the ammeter measures it. After measuring it, there's a resistor here, so the potential difference across the resistor, the voltmeter will tell me, and it will come through this side. This is the AC that I need. So this is a resistor that has been connected in the AC circuit. So what happens to the current and the voltage in in an AC circuit with a resistor in it? What happens to the current and voltage? They are always in phase. The current and the voltage in a resistor are in phase. What it means is, if I were to plot the graph, please don't mind my graph, this is supposed to be a straight line. Plot the graph of voltage against time. Voltage against time. Don't forget I said it's going to be a sine graph. Okay, if I plot, okay, let me mesh two graphs. Let's say I plotted another one. This time is current against time. It will be the same flow, the same thing. Anyway, this one stop in the graph. That is where the current also will stop there. So this one is for voltage against time. This one is for current against time. The same thing, the same thing. No one is ahead of anyone. No one gap each other. They are in the same phase. That's the language we use. Or they are in step. The same phase. The same phase. Or you can say they are in step. So both the current and the voltage are in the same phase. And don't forget, from Ohm's law, V equals to I arrow. Don't forget that formula, Ohm's law. V equals to I arrow. Yeah, where the V stands for potential difference and the I is current, arrow is resistance. So if we put V equals to V naught sine omega t, I think you have seen this formula before somewhere. V equals to sine omega t. Okay, or let us make if we put it here for V, okay, that's V naught sine omega t equals to I arrow, because V equals to V naught sine omega t in AC. So I can substitute it if I like, especially if they give you the parameters. So if I make I the subject of formula here is going to be V naught sine omega t over arrow. Please take note of that. V naught sine omega t. Okay. Even this I self can be replaced with I naught sine omega t. So I can write here I naught sine omega t. So you see, so we can have, please take note again, we can have V naught sine omega t over arrow equals to I naught sine omega t. I'll be learning all these formulas. The omega angular velocity, don't forget time. The V is maximum potential difference, maximum current, angular velocity, that is omega. You want to put omega there now as 2 pi f. You have V naught sine 2 pi f t over r equals to I naught sine 2 pi f t. You'll be learning the formula. Learn them, cram them. Learn them. And if we connect, the voltmeter, the ammeter is connected in the circuit. And I said, what the voltmeter and ammeter measures, actually, when the voltmeter measures, they say it has measured the potential difference. When the ammeter measures, say it has measured the current. What the voltmeter and the ammeter is measuring is the steady current or the steady voltage, and it is called the RMS value of voltage when it is steady. So even if from Ohm's law I equals to V over R, I can also see that the current that this guy is measuring is the steady current. Then the voltage being measured is the steady voltage. Let me write. I wanted to write S just now before over R. So please take note. So I said both the current and voltage, they are in step. They are in the same phase. Look at the graph of V against time for a resistor. The voltage inside, or if you plot the current inside with time, the voltage with time, the graph will go the same way, no difference. So they will produce in the same way. Anywhere the voltage stop, that is where the current will also stop. Please take note of that. Now, okay, gotten these formulas here. And we said they are in step and in phase. What it means is that both of them attain zero level, maximum level, different, any value, maximum value, zero at the same time. So the current start from zero, voltage started from zero. When it reach here, this one has reached here. When it gets to its maximum current, which is this place, this one too has attained its maximum current. When it is at zero, this one too started from zero. So when they say they are in the same phase, it means both of them attain a maximum, zero, and minimum value self at the same time. So that is for resistance in AC circuits. So the current and the voltage are in the same phase or the same step. Okay, let's go to capacitance. What happens in a capacitance? Capacitance in an AC circuit. Okay, let me draw it. Capacitance in an AC circuit will have let me put ammeter here like I did the first one, and there will be a voltmeter to measure the potential difference across the capacitor. So from here, let me draw the circuit. Okay, let me put the AC here to show that it's varying, it's changing. So this is a capacitor, this is a voltmeter. Okay, I put ammeter here to check the current. All right, now in a capacitor, the current and voltage, how do they work? How do they move? Let me show you how it is. I'm going to use as if I'm plotting. If you plot the graph of voltage against time, this one is let me say this side is for current. Let's say this first graph now. Draw a stop here like this. Now drawn down one like this. This one is current against time. Now, when the voltage start from origin like this, when the voltmeter start from origin like this, go like this, go like this, go like this. This linear barrel. Go like this. The current does not start like that. The current does not start like that. The current is ahead by 90 degrees. You know, the current is ahead of the potential difference, ahead of the voltage by 90 degrees. So let me start the graph from here now. You know, if I start from here now come like this. Now come like this. Like this. So if you observe now, the current is already here. This one started from here. This one has already gotten up like this. You see now, it's as if this one has already attained its maximum. You know, from here to here is amplitude now. In waves that time, when we're doing amplitude, from here to here is the maximum. From here to here, maximum. So it has attained its maximum. The thing is also like, let's say, you go like this. From here to here, in wave, from here to this place is the amplitude, which is the highest vertical distance reached by the particle from its equilibrium position. So in this AC now, from here to here now, is the peak current. So peak current. You know, from here to here 90, from here to here 90. So that's why here is 180. I'm on the straight line. So this is 180. So this one now has already attained this place, and this one is, look at voltage trekking against time. So in a capacitor, the current is ahead. In fact, the current leads. That's the word we use. The current in a capacitor leads by 90 degrees. 90 degrees is leading who? He leads the voltage. He's leading the voltage. Leads the voltage of the capacitor by 90 degrees. Leads by 90 degrees. So that 90 degrees also, you want to use as pi over 2 radian. In terms of radian. Radians. Okay. Or one cycle is 360. Let's divide 360 by 4. That's 90. So 1/4 of a cycle. Any of them. So who is ahead now? Current is ahead. So current is ahead of the voltage. The current, let's say the current is somewhere here now. The current is the capacitor. Let's say it's coming like this. Now, where is the voltage of that capacitor? See where it is. From here to here is 90 degrees. You saw it in the graph just now. So, for capacitors, the current leads. The current is ahead by how many this now? That's 90 degrees ahead. So the current leads by 90 degrees. Again, don't forget this formula that says V equals to V naught sine omega t. Then current equals to I naught sine omega what now? Omega t. So who is leading now? Current is ahead, Abi. by 90 degrees, or pi over 2 radian. So this guy and this guy, they are not, this guy has gone ahead. So let me add pi over 2 to it. So if the voltage is having this value, look at what current is having. Please don't forget. See another formula there. So this is what is happening there. The current is ahead by 90 degrees. Are you seeing the formula there? Current is ahead by 90 degrees. Please take note of that. So the capacitor, you see, also opposes the flow of current. You should take note of that. Capacitors also has their own, like I was explaining to you about resistor. There is not only resistor that opposes current. Based on the materials the capacitors are made up of, they still have the ability to resist current to a very great level. If you observe our galvanometer conversion that time, we considered some things there. You know, when we're trying to compare potentiometer and voltmeter self, we said that for the voltmeter to work, it will collect current from the circuit to work. We said for the voltmeter to work, it will collect current from the circuit for the voltmeter to work. So it's not going to measure the EMF of that distance. You know, please take note of that. And don't forget that I equals to E over big arrow, that's external resistance plus internal resistance. There the E stands for the EMF of that battery. Although that's not we are going to, just let me just ship that in. So the capacitor can still oppose current. The resistance offered by a capacitor is called capacitive reactance. We don't call it resistance again, reactance, because it's not normal resistance. So the resistance, well, let me not even use the word resistance. Let me use the opposition. The opposition, it will look different now. The opposition offered by a capacitor to the flow of current in a circuit is known as capacitive reactance. Capacitive reactance. There's where we used to write reactance X to show that it is capacitive reactance, as in the opposition from capacitor, put C there, XC. And the formula for XC equals to 1 over 2 pi FC. In case you want to calculate the capacitive reactance, this 2 pi F is omega. So crown this one. So XC equals to 1 over omega C. This is capacitance. And sometimes you might get the equivalent capacitance for series or parallel connection. So an opposition offered by a capacitor is given by that formula X equals 1 over 2 pi F. Now don't forget from Ohm's law that V equals to I arrow. Now if you are talking about opposition now by a capacitor, we'll not put arrow again. No. You write XC. You write XC. Another formula. Cram all these formulas. For the parameters, when the parameters are given to you now, you'll be able to use it to solve. So V equals to IXC. This one is the opposition to the flow of current offered by a capacitor. Don't forget this formula. We said the current lead. So if V equals to that value, I is plus pi over 2 or plus 90 degrees. So we are here now. V equals to I x c. Are you there? So it is from Ohm's law. That is where we are getting this in there from Ohm's law. Now, okay, let's take one example. So it means that Ohm's law also applies to a capacitor. The arrow was replaced with XC. So this XC is in ohms, was his opposition. This one, SI unit for XC, is also ohms. Please take note of that. Okay, let's take one question, one example. It says a 2 microfarad capacitor is connected directly across a 150 RMS. I'm using RMS now because we have known that it is a steady voltage now. RMS 60 Hertz, 60 Hertz, AC source, AC source, AC source. Okay. Question now says find what? The RMS value of the current. Here it says the RMS value of the current. Then B says peak value. Peak value of current. Peak value of current. Alright. So don't forget the equation. Don't forget the formula there. You have for the capacitor XC equals to 1 over 2 pi FC. Don't forget that. So it will substitute now. XC becomes, so it's normal simple calculation, 1 over 2 pi, or 2 times pi rather, 2 times pi. Pi is 3.14 times 60 times micro is 10 raised to the power what? Minus 6. When you do everything, my XC will now be 1324.4 ohms. When you calculate it, when you push your calculator, that is what you're going to have. That is the XC. Okay, don't forget again that V equals to IXC, because the word has to calculate the peak value of the current, and I said this I is RMS. So I RMS equals to V over XC. So the V here is, according to the question, where is the voltage? Okay, 150 volts all over XC, which is 1324.4. Dividing it, you are going to have the current there, which is the RMS current, as 0.113 ampere. Then for the peak current, don't forget peak current, 0. Don't know, but we know peak current. Look at it, okay? Let me just show you. Peak current is, look at it there. The formula is IRMS equals 0.707 I naught. So if I want to make I naught stand alone, which is peak current I naught now be equals to, let me even use that root 2. Cross multiply. Let me use that root 2. So you have root 2 times IRMS. So we have, when you times it, you're going to have 0.160 ampere. That is what we're going to have. So that's for capacitors in an AC. That is how you apply the formula. So you see the application of the formula is direct. Okay, let's see for inductance. Inductance in an AC. This time around, okay, let me still put the ammeter there. The voltmeter here. Let me put an inductor here. Got the symbol of inductor. So you have okay. So it's for inductor. So this voltmeter will measure the potential difference across the inductor. Now, this time around, who is supposed to lead? Can you guess? This time around, it is the voltage in that inductor. Symbol for inductor is L we use. The voltage is supposed to be ahead of the current by 90 degrees. So here, it's 90 degrees. 90. So this time around, the voltage of that inductor potential difference leads the current IL by 90 degrees or pi over 2 radians. Or 1 over what? 4 cycle. Okay. So it means that that formula will change. V equals to V naught sine omega t. Now is leading now. Voltage is leading. Okay, current normally equals to I naught sine omega t. Who is leading? Voltage is leading. So I can put plus pi over 2 here. I can even put minus here. To show it is, we can say lagging. If you don't want to use the word voltage leads current by 90 degrees or pi over 2 radian, you can still say that the current is lagging by pi over 2. So we understand the English. Lagging, Lagging. It's lagging by 90 degrees. So an inductor, that's for inductance actually. An inductor can see oppose current. That opposition offered by an inductor is what we call the opposition offered by an inductor is called inductive reactance. Inductive reactance. Okay, so instead of V equals to IR, you can have V equals to IXL. This XL now, based on the fact that it is inductor, that is why it is like that. Then that XL has a formula too. XL, okay, for capacitor it is 1 over. Okay, it's not. This one now is just 2 pi FL. No need for 1 over again. You know, inductors in series or whatever, it's the same. Inductors in series and parallel, the same formula with resistors. So this L there is inductor, and the SI unit for inductor is Henry. So inductive reactance. So reactance now is an opposition offered by reactor. Let me define it. Reactance is the opposition to the flow of AC offered by a capacitor or an inductor or both. All right, let us see a good question here. Now, if you hear of impedance is Z, is opposition offered by a resistor. This one, now resistor is involved, capacitor and inductor, and the symbol for impedance is Z. So V equals to IR we change to V equals to IZ to show that this one now involve resistor, capacitor and inductor. So the overall position is also measured in ohms. Please take note of that. Okay, let's see this question now. This question says find the what now? Find the impedance inductive reactance across an inductor 0.2 Henry inductance when an AC voltage of 60 Hz apply across it. if the voltage is given by 150 sine 120 pi t. Calculate the RMS and peak values of the current. Very simple. For that inductive reactance, XL equals to what? 2 pi FL. So let us substitute there. I'm going to have 2 pi times 60. It says 60 hertz times L in ohms. We don't know the L. So I have 120 pi L. Okay, they gave us L to be 0.2. That's 120 pi times 0.2. 20 times 0.2, which is going to be 75.40. So take past 3.142. You're going to have that. Now, don't forget that V equals to what? V naught sine 2 pi ft. And they gave us an equation that V equals to 150 sine 120 pi t. So F from here, if we compare, that's 2 pi ft equals 120 pi t. 120 pi t by comparison. This will cancel this. This will cancel this. Because there's F here. Okay. Sorry, F becomes 120 over 2, which is the 60 hertz. I think they've given us 60 before. Okay. They've given us before. So, okay, if we compare again, V naught equals 150. V naught equals 150 volts. Okay. So let us get our RMS. So V RMS, don't forget, it gave us V to be what? Again, 150. So it will be 150 times okay, VRMS, sorry, equals to be 0.7 V naught. Let me remove the 0.7 inside. So then I have 0.7 times V naught, which is equal to 105 volts. Don't forget IRMS equals to VRMS all over XL, which is 105 over 75.4. So the IRMS there equals to 1.39 ampere. Okay. And okay, we've gotten that one. Then the other one now is the maximum or peak current. I naught equals to V naught over XL, which is V naught is 150 over 75.4. Please take note here. Yeah, I said VRM equals to 0.7. I remove the 0.7 V naught. I want to get my VRM because it's steady one that I will use. That's why I use it here. That's what it has to do there. Please take note. So have your I naught when you divide. I naught will now be 1.99 ampere. Okay. So with that, we have done that calculation there as stated there. Please take note of that. What I'm trying to explain to you here, where I wrote here is that place. There was a place I wrote peak value of current. Look at it. Higher RMS of current is equal to peak value of current over root 2. So we can do the same here. Look at it for voltage. I did it here. Here. Look at it. V RMS will now be equal to 0.707 V naught. Just as you have I RMS just now to be 0.707 I naught. So the same thing. You can write it as RMS equals to 0.70 I naught. So anyhow to put it, but this is the answer to that.